Conference. May I kindly ask you to take your seats so we can start our today's program. I hope you enjoyed yesterday evening's welcome reception and the poster session, and you are looking forward to our today's program. We will start with a welcome remarks by Mr. John Elbon, Vice President and General Manager, Space Exploration, the Boeing Company. Mr. Elbon, please.
Thanks, Christian. So good morning. Welcome to day 2. Congratulations to Mike Griffin and the AIAA, Bernd Furbacher and the AIF for a great day 1. We're off to a good start. And as I say, welcome to day 2. So I'm excited to be here at this conference to discuss the latest thinking in space exploration, the capabilities that we have, the ones we need to develop to make exploration beyond low Earth orbit possible. Yesterday, the world's leaders talked about space exploration initiatives from a global perspective. We discussed the status of our capabilities relative to technologies, destinations, timing, and options for various pathways. And today we'll look deeper into those topics, getting to Mars, the technical capabilities, partnerships, roles of government and industry and commercial providers necessary to continue the exploration. And we'll discuss the priorities and roles of human and robotic missions. Can robots play a precursor role for human exploration? Can humans and robots work together? Yesterday afternoon in the plenary session, we discussed competition and cooperation. And I couldn't help but think, as we were having that discussion, how the International Space Station has been a real catalyst for kind of driving cooperation among competing entities around the world. I think it's time now to leverage those relationships, to add new ones, and to focus that capability on the next grand adventure of human space exploration. And so that's what we're here to talk about today. So let's go forward and make that so. Again, welcome to day 2. Get engaged, have some good dialogue. Thank you.
Thank you, John. We now move on to our first keynote, and it is my pleasure to call up to stage Mr. Walid Abdalati, NASA Chief Scientist. He will introduce our today's speaker.
Thank you. I appreciate the opportunity to be here and make a few introductory remarks. I really think it's an exciting time to be gathering this community together because I very often in my job get to stop and pause and reflect on the fact that we are at a point in human history that civilization has dreamt of since the beginning of humankind, since humans could first maybe not walk upright but look upward perhaps to the stars with wonder about what it's like there. Is it possible to go there? What can we learn about it? And over the last few decades, we've had tremendous progress and the tremendous privilege of being able to do these things. And if you go back thousands and thousands of years, this really is a turning point in human history, these few decades and the decades that come. So this is an important conference. This is a great opportunity for me to stop and share that view with you, although I'm sure you all have that yourself. But the key to these successes, as we all know, is commitment and partnerships. Partnerships across nations and partnerships with industry, partnerships with academia and the like. But it's a wonderful time because we're exploring space. We are on the brink of, or have made, some incredible discoveries. We're pushing human space flight, the human exploration frontier, in low Earth orbit with the space station, the remarkable partnership and achievement that represents, looking beyond to go to other destinations with other capabilities and continuing that forward-moving spirit. And I like to say we're growing into space. And the launch of the Falcon 9 on Tuesday was one, pardon me for saying buzz, but I believe a giant leap for growth into space. And I think it represents an incredible opportunity and incredible progress. At the same time, we're growing into space and pushing frontiers on the scientific front. You know, as chief scientist, again, I have a lot of privileges, and one of them is to share with people that we are looking toward the edges of the universe and back to the beginning of time as we understand it. We're exploring the sun that fuels life on Earth. Life on Earth, the bottom of the food chain may be the plant, but the first element of that food is the photon. So exploration of the sun. We're understanding the planet we live on, and perhaps more importantly, the planet we're going to leave behind to our children and grandchildren. And we're understanding and exploring our celestial neighbors, giving us insights into the origin of our planet, our place in the solar system, our place in the universe, the potential for life elsewhere. And I actually think there's been no scientist more instrumental in fueling that than our next speaker, Dr. Steve Squires. And his focus, you'll hear from the bio, or if you've read it, that he's been involved in a lot of things in our solar system. All the things you can do from Earth, I suppose. But his greatest, or I'd say the most of his attention has been paid to Mars, to exploring Mars, our red neighbor, and trying to unlock the secrets that it may hold. Really to provide unimaginable, perhaps, insights into our own civilization, our own existence, our own being. So a few fun facts about Steve Squires. He's the Goldwin Smith Professor of Astronomy at Cornell University and is the principal investigator for the science payload on the Mars Exploration Rover project. We all love spirit and opportunity. Received his PhD from Cornell in 1981 and did a 5-year stint at NASA's Ames Research Center before returning to Cornell as a faculty member. His main area of scientific interest has been Mars, but also the moons of outer planets. He's participated in many, with a capital M, NASA planetary exploration missions, including the Voyager mission to Jupiter and Saturn, the Magellan mission to Venus, and the Near-Earth Asteroid Rendezvous mission. In addition to his current work on the exploration rovers, he's co-investigator on the 2003 Mars Express, 2005 Mars Reconnaissance Orbiter, 2011 Mars Science Laboratory mission, and also the Mars Odyssey mission. You're sensing a theme here, Mars, 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 and the Cassini mission, the outlier to Saturn. Dr. Squires recently chaired the Planetary Decadal Survey for the National Research Council, which laid out a vision and priorities for planetary science at NASA. He has many service functions to the agency, including his current appointment as the chair of the NASA Advisory Council, and has been recognized with numerous distinctions from the American Astronomical Society, AIAA, American Astronautical Society, the National Space Society, the Franklin Institute, and others. But besides being an outstanding and accomplished scientist, as his record and awards really make clear, Steve really brings something so much more to his work and to the space exploration in general. And this is why I wanted to come here and stand here and introduce him, because I watched him when I think it was Opportunity landed. You don't know that, but I was at JPL and I was looking into the room, and you know, the excitement, the energy, the realization of years and years of investment, the appreciation for all the science that brings was incredible. And he brings a passion, a curiosity, no pun intended, a true sense of wonder that is contagious. And to share some of that wonder and some of the science, he's agreed to give us some of his time. So without further ado, Dr. Stephen Squires. Thank you.
All right, well, thank you very much, Waleed. We got the slide up. Good, okay. So this morning, for the next 45 minutes or so, what I'm going to try to do is three things. First of all, I'm going to start off by just kind of summarizing where we stand scientifically on the exploration of Mars, what we have learned. As you will see, the last 15 years or so have been just astonishing in terms of the growth in our knowledge about Mars. I'm going to talk then about what I think could come next at Mars, and finally, and most importantly, what we need to do if we hope to achieve that. Now, I want to start with a little bit of history. Okay, contrary to what you may have read in the papers, Mars Global Surveyor, Mars Odyssey, all these other missions that you can list did not discover that there was once water on Mars. Okay, that honor belongs to Mariner 9, all the way back in 1971. And we tend to forget this, but there were missions before this golden age of Mars exploration that really laid the groundwork. My point here is that we're not just discovering water on Mars. What we're doing with our current missions is adding a depth of knowledge way beyond just that. And I'll get to that, but I want to just lay the historical groundwork first. One thing that you hear about on Mars is the big floods, right? Big outflow channels. These were discovered by Mariner 9. Okay, this Mariner 9 image shows channels that were formed by a flood that's the equivalent of a couple of hundred Amazon rivers all cutting loose at once, roaring across the Martian surface. Mariner 9, 1971. The really exciting discovery from Mariner 9 was actually not the big floods, but it was the little ones. It was the little trickles of water flowing across the surface. These are some dendritic valley systems. And in order to form these, you have to have conditions that are very different from Mars today. Mars today is cold and dry and desolate. This tells us that in the past, Mars was different. It was warmer and wetter, and that was what formed really the basis for this program of exploration that we've had going forward, was this discovery. Big deal recently has been the fact that there are these gullies on crater walls that have apparently been active quite recently. Even these gullies, not their recent activity, but the existence of the gullies themselves was discovered by Mariner 9. So there was a lot that we did way, way, way back in the 70s to lay the groundwork for what's happening at Mars today. Not long after that, of course, came Viking. Magnificent mission, maybe overreached a little bit scientifically. The objective was to find out if there were microbes living in the Martian soil. The answer was probably not, at least at this particular spot. But it was the first successful landing on the surface of another planet. Beautiful images of the surface. It sort of opened our eyes to what it's like to be on the surface of Mars. And then, of course, there were also, largely forgotten, but one of the real triumphs of this mission was there were two orbiters. And the orbiters provided magnificent global coverage of the planet. Well, after that, things started to get serious. And now you move forward into the 90s, and you get to the Mars Global Surveyor mission. This was part of the recovery from the loss of the Mars Observer mission, carried 5 of the original 7 instruments that were on Mars Observer, and this mission was a triumph. This is actually one of my favorite pieces of data from this entire mission. It's a little crazy looking, but what this is a map of magnetic anomalies on the Martian surface. This is remnants of an ancient Martian magnetic field frozen into ancient rocks on the surface. Now today, Mars does not have an intrinsic magnetic field. Okay, there is no magnetohydrodynamic dynamo inside the planet that is operating today, creating an intrinsic magnetic field. But what this says is that in the past, there was. And if you look at the distribution of these crazy magnetic anomalies on the surface, you see that they're not everywhere on Mars. There are some places, but not others. Well, it turns out the places where you find these are the old places, the oldest rocks. What this says is that in the distant past, Mars had a magnetic field and then it shut off. Now, one of the important things about a magnetic field is that a magnetic field provides a protective bubble, if you will, around the planet. Okay, it protects the planet's atmosphere from the solar wind. The solar wind gets diverted around the magnetic field. If you have a magnetic field, you have that protection. If the magnetic field goes away, now the solar wind can impinge on the atmosphere and can strip it away. And so when you say, what happened to Mars? Why was it warm and wet in the past, and why is it cold and dry today? Well, in the past, if it had a dense atmosphere, you can have a greenhouse effect, warmer climate, shut off the magnetic field, atmosphere gets stripped away, greenhouse effect goes away, and you get the cold and desolate world that we have today. So this is a critical piece of information here. One of the big experiments on MGS was the altimetry experiment. This is the topographic map of the entire planet, exquisite detail. This doesn't even show all the detail in it, but it shows some of the big outflow channels. You can see the blue stuff there emptying out onto the northern plains out of the Valles Marineris. So magnificent data set. One of the really exciting experiments on MGS, and this was something that really revolutionized our understanding of the planet at a local scale, was MOC, the Mars Orbiter Camera. This is a magnificent camera, about 2 meters per pixel resolution, and it really gave us some compelling information about things that have happened on Mars. So this is a place, this was one of the landing sites. This is one of the candidate landing sites for MSL. It was not the one that was chosen, but it would have been a darn good one. This is a place called Eberswald Crater, and I'm going to blow up one little portion. What you're seeing here is what you'd call a distributary fan. This is a place where water flowed into a crater and built a delta. And you see classic forms here. What you can see there on the right is a meander, a cut-off meander. Water flowed here in just the same fashion that you see on Earth. Here's another piece. Here what you're seeing multiple episodes of flow. Look at those things cutting across each other. This happened and then that happened. There were multiple episodes. So this was an extended period of water activity. Okay, all of this revealed by MOC on Mars Global Surveyor. Then we send MRO, Mars Reconnaissance Orbiter. That one has a resolution of 30 centimeters per pixel. This is that same cutoff meander in color at 30 centimeters per pixel. We can do real geology on the surface of Mars with these orbital assets. Just magnificent stuff. So we're not guessing anymore. We know. Okay? The same orbital capabilities have been extended out into the infrared. And now from orbit, we can also do magnificent compositional remote sensing. This is a particularly important map to me because this was the map that caused us to select the landing site that we chose for the rover Opportunity. This is a map of hematite. This is determined from orbit by the thermal emission spectrometer on the Mars Global Surveyor spacecraft, and red on here is high concentrations of hematite. Now, hematite is an iron oxide. Okay, it's a mineral that is typically, it's found in rust. It's a mineral that usually forms as a result of the action of liquid water. And so that red spot that you see right in the middle there, that bright red spot, that's Meridiani Planum. That's where we chose to land with Opportunity. And it's like a chemical beacon visible from space saying, hey, come land here. Water may once have been here. Okay? But there's been other wonderful compositional remote sensing as well. This is one of the biggest discoveries at Mars in the past couple of decades. This is from the Omega experiment, a spectrometer on the European Mars Express spacecraft. The stuff that you see in blue there is what you call a phyllosilicate. It's a clay. These are clay minerals. Now, the importance of clays is crucial to understand this. Clays form as a consequence of the action of water, okay, just as is the case with the hematite and some sulfates that I'll talk about a little bit later. But the key thing about phyllosilicates, about clays, is that they can only form under a neutral pH. That's really important because a lot of the minerals that we find on Mars, and I'll give you some examples in a few minutes, require very low pH. There was a lot of, people run around saying water on Mars, water on Mars. Well, a lot of it was actually sulfuric acid on Mars. Okay, a lot of the water was very, very low pH. But the critical thing about the clays is that they can't form at low pH. You need a neutral pH to do this. Okay, and neutral pH is what life likes. Okay, it's very hard to get the chemistry of life going at a pH of 3 or 2 or 1. Which is what's implied by many of the minerals that we find. But this stuff, this is a pH of 7 or 8, okay? And so finding these, and by the way, these clay minerals are in the most ancient rocks. They're not everywhere. They really tend to be concentrated in the oldest stuff on Mars. Okay, so this wonderful discovery from Omega on Mars Express told us that there was neutral water, neutral chemistry water, in the ground coming to the surface long, long ago on Mars. But we're adding more detail beyond that. It's not just there were clays. We can talk about what kinds of clays they are. The next really nice infrared spectrometer to fly to Mars was an experiment called CRISM on MRO. And this one has the spectral resolution and the spatial resolution necessary to distinguish different clay minerals from one another. What you see here, two different clays. One's an iron-bearing clay, one's an aluminum-bearing clay. Okay, and you can distinguish them spectrally. The bumps and the wiggles in the spectra are different enough and the instrument's good enough that we can tell them apart. And then what you do is you go and map them on the surface. Again, this is back at Marthalis, the same place that I showed you before. And now you can map where the iron-bearing clays are, where the aluminum-bearing clays are. And you can take that information and you can combine it with topography, and you get compositional stratigraphy. You know, these clays are on top of those clays. It's magnificent stuff. Okay, so it's not just water on Mars. We're really, really adding a great deal of depth to our knowledge here. It's not just clays either. This is from the Themis experiment on the Mars Odyssey spacecraft, and here what you're seeing is chloride, probably sodium chloride salts on the surface. Water evaporated away here and left salt deposits behind. This is one of my favorites. This is an experiment that I was fortunate to be involved in. This is a map of the concentration of water, effectively. It's actually hydrogen. But this is the concentration of hydrogen, probably equivalently the concentration of water, at the Martian surface. And what you see is at low to mid latitudes, there's a modest amount, and this is probably mostly water of hydration. There are a lot of minerals, sulfates primarily among them, that can contain a substantial amount of water locked up in their crystalline structure. Okay, and at the low latitudes, you find a lot of this. We've seen the same things with the Mars exploration rovers. But look at the high latitudes. You can just barely see it on the upper and lower fringes of this map, but it gets really rich in hydrogen, really rich in water. What you're seeing there is ice. Okay, and what we hypothesized from this data set was that if you go poleward of about 55, 60 degrees latitude on Mars, you should find high concentrations of ice within, 50 centimeters or so of the surface. Now that was demonstrated dramatically by this vehicle here. This is the Phoenix lander. The idea behind Phoenix was that you would land at a high latitude near the polar regions. You would use that robotic arm that you see to dig down below the surface, and if you're lucky, maybe you would actually find some ice below the surface. Well, it turns out you literally scratch the surface. You just scrape it, and bang, there's the ice. In fact, if there was a beautiful image, I didn't include it here, but the exhaust from the rocket motors, when this thing touched down, blew away 5 centimeters of dust, and underneath there was bright white ice. Okay, so there's a lot of ice in the polar regions on Mars. Let me talk a little bit about Spirit and Opportunity, some of the discoveries. We'll start with Spirit. Spirit landed in that big blue crater that you see in the middle of that slide. That's Gusev crater. It's 160 kilometers in diameter, 16 degrees south latitude on Mars. The reason we chose Gusev as a landing site is you can see to the south there's a great big dry riverbed flowing into that thing. So our hope was that we would find some ancient sedimentary rocks laid down billions of years ago in a Martian lake. We did not, but we found some other pretty cool things as well. This is one of the nicest discoveries from the whole mission. About 800 sols, 800 Martian days, into Spirit's mission, the right front wheel failed. And after it failed, it really severely affected our mobility. A vehicle that used to happily do 100 meters in a day, a good day was 5 meters, and we'd have to drive backwards, dragging that dead wheel through the soil. But the silver lining to that cloud was that this dead wheel would dig this marvelous hundreds of meters long trench through the Martian soil. And every so often, something wonderful would pop up on the floor of that trench. And this is a picture that we took one day. We were driving through a little valley, and we took this image, and the soil in the bottom of the trench popped up as bright as white snow. Okay, this attracted our attention. We went over and measured its composition with our alpha particle X-ray spectrometer, and this stuff is 91% pure silica, SiO2. This is not quartz, this is not beach sand. We looked at it with our other instruments as well. This is opal. This is hydrated silica. This is the kind of stuff that you form in a hot spring environment or in a volcanic fumarole. And you can go to hot springs, you can go to volcanic fumaroles on Earth, and they are teeming with microbial life. Now, this doesn't say that this was a place where there was life, but this is a place, this silica deposit in this little valley tells us that this was once a habitable environment. Of course, we named this place Silica Valley. This is another big one. This is a rock called Comanche. And this is an interesting story. This is some data that was sitting around on the ground for about 2 years before we figured it out. But this rock is made of roughly 25 to 30% carbonate, iron and magnesium carbonates. It's not calcium carbonate. It's not limestone. It's other carbonates. But carbonates have been something people have been expecting to find on the surface of Mars for a very long time, and we finally did find it. These are the first massive carbonate deposits ever discovered on Mars. This is the Opportunity landing site. The data on the right there, that's that hematite map that I talked about. Blue is lava, but the red and the green and the yellow, that's high concentrations of hematite, and that's what brought us to Meridiani Planum. When we landed, we discovered to our astonishment that the water activity that had deposited the hematite had done it in a sort of a strange and peculiar way. If you look at that picture on the right, what you see is that there are these little round things embedded in the rock like blueberries in a muffin. In fact, we called them blueberries. And the blueberries are hard and the muffin is soft and the muffin erodes away and the blueberries fall out, and the blueberries, it turns out, are made of hematite. What these things are, these are concretions. Okay, concretions are found in sedimentary rocks on Earth where the ground has been saturated with liquid water. Okay, and there's some mineral like hematite that's dissolved in the water, it's supersaturated, it wants to precipitate out. And what happens is as it precipitates out, it builds this little hard spherical nodule in the soil, in the rock, sort of like the way an oyster builds a pearl. And so what this is telling us is that the ground was once soaked with water at this location. We also found some bizarre and fascinating chemistry in the rock itself. The bedrock here is made largely of sulfate salts. There's calcium sulfate, a lot of magnesium sulfate, and it's about 10% in iron sulfate called jarosite. This is some data from one of our spectrometers, and that yellow double peak in the spectrum you see there, that's the jarosite. Jarosite is a fascinating mineral. It only forms under low pH. It's not even stable above a pH of 5, and it typically forms on Earth at a pH of 3 or 2 or 1. Okay, so this is a place where acid, sulfuric acid, bearing salts, came to the surface, evaporated away, and it left these salt deposits behind. Again, the point here is that we're not just discovering that there was once water on Mars. We are adding an incredible depth of detail to our understanding of what the planet was like long ago, the details of the chemistry, the details of what the water was doing. This is very recent. We just published this in an issue of Science that came out 2 weeks ago. Okay, so this was just discovered this past year by Opportunity. This is a vein of gypsum. Gypsum is a calcium sulfate. It is water-bearing. This is very pure gypsum. As near as we could tell, this is just pure gypsum. There's nothing else here. Okay, gypsum veins are common in sedimentary rocks on Earth. They form in one way and one way only, and that is that water percolating through the cracks is supersaturated. It precipitates out gypsum. And so this is a place where a crack opened up, water flowed through it, and gypsum was deposited. These are places where you can find microfossils. Okay, these are places where if there was something living, it can be trapped within that precipitated matrix and preserved for a very long time. I would love to have a piece of this back on Earth. Now, we got something big coming too. In August, we're going to see the the landing of the Mars Science Laboratory. This is a magnificent piece of hardware that lands in just the scariest way you've ever seen, but we're all looking forward to it. Absolutely fantastic payload, okay? I won't go through the whole payload, but just a couple of highlights. This one carries an X-ray diffraction instrument. X-ray diffraction is the gold standard in mineralogy. Yeah, you can do great remote sensing, mineralogy with infrared devices and so forth, but when geoscientists really want to know what a rock is made of on Earth, what they do is they do X-ray diffraction, and this vehicle is capable of doing that. So it's going to do wonderful, definitive mineralogy beyond anything we've been able to do with our rovers. Another experiment, which I'm tremendously excited about on this one, is one that does organics. We're going to be able to drill into rocks, this deep, pull out powder, put it into this thing, and find and characterize organic molecules at the parts per gazillion level, okay? It's going to be just wonderful, and this is just an unprecedented capability. Now, if you have a vehicle with this capability, you need a landing site to match, and we do have one. In fact, it was a tough problem selecting the landing sites because we've learned so much now. We know so much about where to go, where the good stuff is, where the exciting science is on Mars. There's just it's just a multitude of choices, and the choice that was finally made here was a great one. It's a place called Gale Crater. You can see it here. The landing ellipse is shown in yellow. If you look just to the south of that ellipse, there's this mound of stuff. Okay, you look at high resolution with that camera that I showed you, the very high resolution 30 centimeters per pixel camera, what you see is intricate fine layering all the way up that mound. It's like 5 kilometers of layered sedimentary rock. And then you look at it with CRISM, the infrared spectrometer, what you see is wonderful compositional stratigraphy. Towards the top of that stack, the younger rocks, you see mostly sulfates, like the kind of stuff that we've seen with our rovers. Towards the bottom, that's where the clays are. So we're going to find a wonderful just geologic history book that we can read page by page as we drive up that section. It's going to be just a fantastic mission. So what comes next? What comes next? As Waleed mentioned, one of the things that we did here recently in the US was what we call the decadal survey. And our decadal survey, as the name implies, is something we do once every 10 years to lay out a decade, or in some cases decades-long plan of space exploration. And we recently completed a decadal survey in planetary science. Decadal surveys it's a big effort. It takes about 2 years. There were more than 2,000 scientists involved in doing this. People wrote white papers. There were a huge number of meetings and so forth. One of the key groups in the US for providing input to the decadal survey was MEPAG. This is our Mars Exploration Program Analysis Group. And this is a group that it's very inclusive. Includes basically anybody in the Mars science community that wants to participate. And MEPAG provided inputs to the decadal survey. You can see what they recommended here. They recommended that we consider, for inclusion in the coming decade, 3 missions. You can see them in red there. TGM is a trace gas mission. This is one to look at trace gases in the Martian atmosphere. NET, that's a Mars network mission. This is an idea I love. It's been around for years. And then the one at the bottom, MSR, Mars Sample Return. And these were the ones that were recommended by the Mars community for a careful look as we move forward and try to assemble a plan. Now, you can't do all this stuff. Okay, there were also groups looking at outer planet satellites and the giant planets and primitive bodies and all across the solar system. But this was the input that we got from the Mars group, and even from MEPAG, the clear and strong emphasis was on Mars Sample Return. Let's see, this is not clicking forward. So could you advance the slides for me? Because now it's not advancing. Okay, here we go. Whoop, back. There we go. All right, great. So on the decadal survey, we looked at a bunch of missions. We looked at the ones that were recommended by MEPAG and others as well. We looked at a Mars Polar mission. We looked at a whole bunch of different things that you could do with that Sky Crane landing system that's being used on MSL. The result was that not just the highest priority Mars mission, but the highest priority mission of all across the entire solar system was Mars sample return. And so the decadal recommendation was that the single highest priority for planetary exploration for the next, not just 1 decade, but 2, because that's how long it takes, is returning samples from the surface of Mars. We have reached the point in Mars exploration, and I hope this came across in that summary of what we know. We've reached the point where in order to make significant further advances, we need to get pieces of Mars into our laboratories, and not just any piece. Okay, if you randomly select rocks off of the surface of Mars, which is basically what meteorites do when they impact the planet and blow stuff off of it and it flies to Earth, you're going to get mostly lava, because that's what Mars is mostly made of. But in a few special, wonderful places, you have these layered sedimentary rocks, like what we're going to be seeing with MSL, like what we saw with Opportunity, that preserve a record of what conditions were like in the past when it was warmer and when it was wetter. And so if we could find those rocks, we can bring them back to laboratories on Earth, we can take them apart molecule by molecule, and we can figure out what Mars was really like and whether or not the planet once supported life. Now, there's another thing about sample return that's important to recognize, okay, and that is that return samples are, in a very real sense, a gift that keeps on giving. Okay, if you look at the science done with return samples from the moon from the Apollo program, the best science ever done with those rocks is being done today by scientists who were not born when Buzz and Neil and the other astronauts collected those samples using instruments that nobody had dreamed of at the time. Okay, so if you can bring samples back, you can apply the best instrumentation on Earth to their analysis for years to come. So how do you do Mars sample return? I'm going to show you one scenario. There are a lot of different ways to pull this off, but there's one way to go about it, and it's a 3-part thing. This is the one that we looked at when we did the decadal survey. The first part is a rover mission, and what it does is it collects and caches a suite of samples on the surface. You don't want to just pick up random rocks, okay? And if anything has been shown by the rover missions that we've done, is that you got to go to the right places, and then once you're there, you got to do some geology. It means you got to really explore the place, you got to find the right materials. So what this rover does is it drives around, it finds the best samples, it collects them, and it just establishes a sample cache on the surface. That's it. Doesn't come back yet. Next mission, this one's a doozy. This one goes and lands close to, so this is nearly a precision landing, lands close to that sample cache. Then it has a little rover that goes over, picks up the cache, brings it back to the lander. The lander carries a rocket. What you do is you take that precious sample cache, you put it into the nose cone of that rocket, and you put into orbit around Mars a spacecraft the size of a coconut that contains those precious Martian samples. So now they're in orbit. Now there's a third mission. Okay, and this is an orbiter, and the job of this orbiter is to find that coconut in the vastness of space around Mars, to rendezvous with it, to gather it in, to put it into a return canister, to then put itself on a trajectory back to Earth and to release that canister so that it lands somewhere and we can pick it up. If this doesn't sound complicated to you, it should. So what does this cost? All right, these were studies that we did during the decadal, and what you can see on the right, I'm not going to go through the details of that chart, but these were computations with conservative cost estimating procedures of how much these different pieces are going to cost. Okay, so the caching rover, we costed out at the time, at least, at $3.5 billion. There might be ways to bring that down, but it's expensive, so let's call that one 3.5. Then you've got this really complicated one with you got to take a launch pad and a rocket to the surface of Mars, for heaven's sakes. Okay, that's $4 billion. And then there's the return mission, comes in at a measly 2.1. Bottom line, 9.6, round it up, $10 billion. $10 billion to do this. Okay, now when we recommended this as part of the decadal survey, we fully recognized that there was no way that NASA was going to be able to come up with the resources to do that on their own. It's too much money. There are no technical showstoppers. All these things can be done, but the cost is prohibitive. You need to find a way to spread the costs around to make this work. It is the single most important challenge that I believe we face, not just in Mars exploration, but planetary exploration, but we can't afford it if we're going to try to do it with just NASA. Okay, so what we need, I believe, is a partnership, an international partnership that can bring this mission about. So what makes a good partnership? Well, you need to have clear roles and responsibilities. That's obvious. I'm a big fan of clean interfaces. You know, you look at some of the partnerships that we've had in the past, and the ones that work well, the interfaces were really clean. One of my favorite examples is Cassini-Huygens. Okay, beautiful division of responsibilities. I mean, the interface, it was basically a bolt pattern and a telecom spec. I mean, yeah, it was a bit more complicated than that, but that was mostly it. Okay, the European and the US parts were really clean, very nice separation. The partnership has to benefit all parties. You can't have one space agency saying, look, this is how it's got to be, and you do this, and you do this, and you do this, whether that's the roles that the other partners want to play. You've got to be respectful of what other partners want to do. So it has to be consistent with the desires of all the partners. And I think it's critically important, you know, different agencies have different strengths. And you want to take advantage of those strengths, and you want to do so in the most efficient fashion possible. This is going to cost $10 billion, and if we're going to spread the cost around, we've got to do it in a smart way. Okay? Now, there are precedents that you can look at for complex scientific undertakings of this magnitude, and in fact, even larger magnitude. This is one of my favorites. This goes way back. This is 1957, 1958, the International Geophysical Year. This was really, you know, I teach a course back at Cornell on the history of exploration, and you ask yourself, you know, how many really, truly international ventures of scientific exploration have there been? This was really kind of the first. Okay, and this was in the height of the Cold War, 1957, 1958. It involved over 60 nations. You can see Russia was involved, the United States was involved, Canada, Indonesia, East Germany, France, okay, Japan, Norway, and many, many others. And the beautiful thing about this was that each nation brought to the table its own capabilities, but because we were making geophysical observations of processes that were global in scope, the whole was more than just the sum of the parts. A lot of great science that came out of this. This image in the background that you see there, that's the Russian Vostok station in Antarctica. It was built as part of the IGY. Explorer 1, okay, the first U.S. Space mission was done. The picture that you see on the right, that's a stratospheric balloon from the Skyhook program. There was just a lot of science that took place, and it was coordinated internationally. It was a wonderful example of how this kind of thing can be done. Best example, of course, is ISS, International Space Station. And this is just, I just can't stress what a magnificent accomplishment this is and how truly international in character it is. And I don't need to hammer that point home too much to this audience. You all know that. This is a wonderful picture. This is from STS-113. This is two American astronauts installing a piece of American hardware. This is the P-1 truss on ISS. You could pick all sorts of pictures for Russian hardware. I picked this one. It shows, of course, both a Progress in the background and a Soyuz in the foreground spacecraft docked to ISS. I picked this one because I love that aurora in the background. But there's Zarya, there's Zvezda, there's Russian hardware all over the station. This is Hans Schlegel from Germany on STS-122. This is an EVA. This is a mission where they installed the Columbus module. That's ESA's Columbus module on station. Here's Kibo. Beautiful piece of hardware. That's Soichi Noguchi inside Kibo doing some experiments. This is the Japanese module. And then here's Chris Hadfield on STS-100, Canadian astronaut putting the Canadian arm in place. This is a masterpiece of robotics. I mean, we've got some pretty intricate robotic manipulators on some of Mars rovers, but look at the end effector on this thing. This thing is it's an amazing piece of hardware. The point is, we know how to do this stuff. We know how to do big, complicated space projects together internationally. And the complexity and the magnitude of this task, I believe, are actually greater than what we need to do to return samples from Mars. So there's a precedent. Now, I don't know the right way to divide up this Mars task. I'm going to leave that to a group like this, but I can at least identify some of the things that we need to return samples from Mars. We need rockets. We need big rockets. Well, I know a lot of space agencies that know how to do that. Okay, here's a Soyuz, an H-2, a Long March, an Ariane, and a Delta IV Heavy. We all know how to launch big rockets. Okay, so there's definitely that capability. Orbiters. Okay, the big successful orbiters at Mars have been mostly US and European. Okay, you see the Mars Reconnaissance Orbiter at upper left. Lower left is the Mars Express. But other nations have been getting into the orbiter game too recently. Only at the moon so far, not at Mars yet. But China, India have had wonderfully successful lunar orbiter missions. So there's a lot of potential there. Landing, that one's hard. The only ones who have landed so far on the surface of Mars has been the US. One of the things that's curious about this picture is you notice we do it differently every time. Never figured that out. One of the things that was great about Spirit and Opportunity was it sounds crazy, but it's still true to this day, we were the only mission to ever attempt to land on Mars using a landing technique that had actually been demonstrated to work. It still didn't help me sleep better at night, but, you know, it was a good thing to do. Anyway, we need an entry, descent, and landing system. U.S. certainly knows how to do that. Rovers, the picture at the upper left I like. It's sort of a family portrait of two rovers that have worked really well and one that we really hope is going to. But the U.S. is not the only game in town when it comes to Mars rovers. Yeah, we're the only agency that has put rovers successfully on the Martian surface, but there's been a lot of work that's been done other places. At the lower left, you've got the Russian Marsakhod rover. This is a design that's been around for a long time. It's a wonderful mechanical design. Makes a real racket when it drives over rocks, but it's a fantastic machine. And then at the right, this is ExoMars. This is a prototype of the European ExoMars rover. I love this picture because everybody makes a big deal about water on Mars, and it's on a beach with the ocean in the background. But it's a fantastic machine. Fantastic machine. And so there's a lot of rover development work that has been done out there. Nobody knows how to do this. Nobody's done this. In fact, the closest anybody has come would have been some of the Russian sample return missions from the moon back in the 70s. I've heard people say, oh, the Mars Ascent Vehicle, it's just a sounding rocket. Well, it's a sounding rocket with some pretty tough thermal requirements and pretty tough delta V requirements. This is going to be a tough job, but I think it's doable, and I can think of a few agencies that can probably do it. And then there's the sample return canister, and a number of agencies that know how to do that too. In the upper left, you see the Stardust sample return canister in the desert in Utah. At the lower right, you see the Japanese Hayabusa sample return canister in the desert in Australia. And lest we forget, down there in the lower left, in a snowbank in Russia in 1972, is the Luna 20 sample return canister that brought 55 grams of material back from the moon. So again, there are a number of agencies, a number of nations that know how to do this stuff. So let me wrap it up. On a bookshelf in my office at home, I have a little glass vial. And in that vial is a little piece of Mars. Okay, and the picture you see at lower right there is a thin section, microscopic thin section through that piece of Mars, through that little meteorite. It was one that landed in northern Africa. Can't learn much about Mars from this, not what you want to learn. Okay, the Martian meteorites that we have, yeah, they came from Mars, but they're all pieces of lava. Okay, and it's not like if we just send enough grad students and enough snowmobiles to Antarctica and we pick up more rocks, we're going to find the rocks that we need either, because what happens is, if you look at those sedimentary rocks, I mean, we've learned this stuff. Okay, we've drilled into sedimentary rocks with our rock abrasion tool with the Mars exploration rovers, and guess what? They're really crumbly and soft. The rocks that we need can't even survive being launched off the surface by an impact. They'll be disintegrated by the impact process. There's no way to get what we want, and what we want is something like that gypsum vein. There's no way to get that without going there and bringing it back ourselves. Okay, it is too tough a job for any space agency to do alone. It costs too much money. I believe we must do it together, and that's the challenge that I put before you. Thank you.
Well, thank you very much, Steve, for a very informative and enjoyable presentation. There have been a few questions. I think we have a little bit of time to ask, so I will read them to you.
All right.
The first is, how will the Maven and other competed science missions contribute when we need such massive collaborations to do the sample return?
Yeah, the thing about sample return is that, as I said, it sucks up so much of the budget that if that's all you do at Mars, there's a lot of other great science you can do at Mars that sort of winds up getting lost. And Maven's a good example. Maven's a mission that is coming up, and the job of Maven is to look in really great detail about the interaction of the upper atmosphere of Mars, the portion of the Martian atmosphere that has always been called the ignorosphere, because we kind of haven't done a very good job of it over the years. But it's a crucial part of the atmosphere because it's the part that does interact with the solar wind, and it's the part that, when it gets stripped away, that's such a driver of the climate. So yeah, I think there's a very important role for competed missions to play to fill in the gaps in what we're doing at Mars. One of the strong recommendations of the Decadal Survey, which I'm pleased that NASA has said they're going to follow, is that Mars missions should be allowed and encouraged as part of the Discovery program. And I know of many research groups out there that are very creative and working really hard to come up with good competed Discovery missions on Mars. And what that'll do is it'll fill in the gaps in our knowledge of this really fascinating planet.
Okay, great. And next question. Do you think we can find fossils of complex organisms using rover-type missions?
Oh, you got to have the complex organisms first. Rovers, you know, finding fossils on Earth is hard. Okay, if you look at the history of Mars, what we know is that the period of time when the conditions were favorable for life, this period when you had water on the surface, particularly water with neutral chemistry, it was brief. You know, it lasted a few 100 million years, maybe not much more than that. You get to 4.0, 3.8, 3.7 billion years, and the fun's over. The climate changed. Magnetic field collapse, atmosphere goes away, and you got a cold, dry world. So you really got to go to the oldest rocks. What that means is life didn't have time to develop to a level of significant complexity on Mars. I mean, you know, people question whether life could ever get started on Mars at all. Well, even on Earth, you look at the fossils that are in the 3.6, 7, 8, 9 billion year old rocks, they're microfossils. They're single-celled organisms. Incredibly hard to find in the field with the best field geologists and best instruments, trying to find microfossils, you know, single-cell microfossils in 3.5, 4 billion year old Martian rocks. Man, that's hard. I think it's a tough one.
Okay. Guess we need to bring some of that stuff back.
You got to bring it back.
Right?
Yeah, hey, here's an idea.
Another question. Well, I'll change it a little, but what is the prevailing theory, if any, on how the magnetic field disappeared from Mars and when?
Okay, when? Very early, 3.5 to 4 billion. The reason it would go away, in order to generate a magnetohydrodynamic dynamo, you need to have an electrically conducting fluid. Okay, you have to have a partially liquid, partially molten core. Mars is a small planet, much smaller than the Earth, contains less internal heat, surface area to volume ratio, etc. Mars is going to cool off a lot faster than the Earth does. And if you run the thermal models, what you find is that the Martian core freezes after a few 100 million years. The core freezes, shuts the dynamo down, you're done.
Okay, and then the last question, a thought question. Do you think we will ever terraform Mars?
Terraforming Mars, yeah. I got to tell you, I'm real skeptical on that one. I'm extremely skeptical on that one. Terraforming basically says that we have both the technology and the wisdom to transform the climate of an entire planet to suit our liking. My feeling is if we can do that, let's do it here. Thank you.
That's a great one to end on. Thank you very much, Steve.
Thank you, Mr. Squires, for this outstanding lecture, providing a really stunning insight and overview of state-of-the-art scientific knowledge about Mars and the exciting plans for future missions. Ladies and gentlemen, let me ask you to join me again in another big round of applause for our keynote speaker. I'm pleased to announce now our third plenary session, which will be dealing with capabilities for human exploration. It is my pleasure to call on stage our distinguished panelists. Mr. Mike Raftery, ISS Deputy Program Manager, the Boeing Company. Good morning. Mr. Alexander Derechin, Deputy General Designer, SP Korolev Rocket and Space Corporation Energia. Mr. Clayton Mowry, President of Arianespace USA. We have Mr. Mowry. Mr. Dan Dumbacher, NASA Deputy Associate Administrator for Exploration Systems Development. Mr. Mark Hampsell, Vice President of the British Interplanetary Society. Yeah. And Mr. Mark Sirangelo, Executive Vice President and Chairman of the Sierra Nevada Corporation. The plenary will be moderated by Mr. Brian Berger, Deputy Editor of Space News. So I hand over to you, Mr. Berger, please.
Okay, thank you. Good morning. So welcome to the first panel discussion of the day. Yesterday we heard from a lot of the senior leadership of the world's space agency, and this morning, with one or two exceptions, I think we have more of an industry-complected panel. And they're going to be talking to us today about the capabilities that are needed to explore beyond low Earth orbit. So we have a great group of panelists, and I'd like to get on with the introductions. To my immediate left, we have Mark Raftery. Mike Raftery. Mike is the Deputy Program Manager of the International Space Station, but he also has a new title right now, which is Director of ISS Utilization and Exploration. And he's with Boeing in Houston. Boeing, of course, is the ISS prime contractor. Next, we have Alexander Derechin. And Mr. Derechin is the Deputy General Designer at RSC Energia, which is the builder of Soyuz capsules and space station modules, among other space systems. Mr. Derechin has 15 years' experience in projects such as Salyut and Mir, Sea Launch, and ISS. All commercial flights have been implemented with his involvement as program manager. And then next we have Dan Dumbacher. And Dan is currently NASA Deputy Associate Administrator for Exploration Systems Development. I think when I first met Dan, he was on X-33 and X-37. And X-37 is in orbit as we speak.
That's true.
Seated next to Dan is Mark Sarangelo. Mark is the Executive Vice President and Chairman of Sierra Nevada Space Systems. Mark was formerly President of Space Dev, which was acquired by Sierra Nevada in 2008. Mark is probably hard at work right now on Dream Chaser, which is a reusable space plane that Sierra Nevada is pitching for NASA commercial crew funds. And I understand that Dream Chaser is going to do a captive carry flight next week. So there's more exciting stuff coming up on the commercial space front. And then last but not least, we have Clay Mowry, who's president of Arianespace Inc., which is the U.S. subsidiary of Arianespace. Clay has been with the company for over 10 years and formerly served as the executive director of the Satellite Industry Association. So the purpose of this panel is to discuss the architectural elements and technical capabilities necessary to get beyond low Earth orbit. But I'm wondering if it's possible to really have a meaningful discussion about architecture and capabilities without talking about destination. NASA, as everybody knows, was told 2 years ago to set its sights on going to a near-Earth asteroid around 2025. But yesterday we heard from Roscosmos chief Vladimir Popovkin and a senior JAXA official about how the moon is kind of the next logical destination for human exploration. And at the same time, there's some compelling arguments out there for putting manned outposts in cislunar space, gravitationally stable Lagrangian points, and even an orbit around Martian moons. So I was thinking before we dive headlong into capabilities, I'd like to ask the panel where we should be going. Is a near-Earth asteroid the best near-term destination for mankind's first trip beyond LEO in 40 years? And I think I'd like to turn that one over to Dan, since Dan is overseeing the design of the systems that will take us out there.
First of all, okay, it is on. Well, first of all, Brian, I think the interesting question is, first, we all recognize that Mars is the ultimate destination. And then, so we have to start with that as the given, and then look at what we need to do and what we need to demonstrate along the way to get to Mars and what capabilities we need to get in place. And then why do we want to go to any of those individual destinations? I think we're still sorting through. We have the direction from the president over a year ago. We are still working through the available asteroids in that kind of time frame, what kind of capabilities are required, and looking at what are the ways and the capabilities we need to demonstrate. And so we're looking at why and trying to sort through the whys and make sure we get a good logical program in place to reach the goals and get that played out. We have a lot of work ahead of us to still sort that out. No destinations chosen other than the Mars. We know we want to look at near-Earth asteroids in the 2025 timeframe, and we'll continue to sort through the whys and the technical capabilities needed to be able to go through that journey.
Dan, how soon does NASA and industry need a definite destination before we start running the risk that you're kind of sub-optimizing some of your decisions because you don't know exactly where you're going?
I think we're trying to work through that right now. Right at this point, we know that we need some initial capabilities put in place, and that's why we have started the Orion and the SLS activities, along with the ground systems work. We know those are necessary capabilities to go anywhere. As we go through the trades and the analysis for why and what the possible options are, and looking at particularly what capabilities we need to demonstrate to execute a human Mars mission, we'll continue to sort that out. Probably in the next year or so, we need to get that. We need to get better definition to that, and that's the approach we're taking now.
Mr. Dreschen, what's your view of near-Earth asteroid as a near-term destination?
It depends. We should take into account constraints we have. The first constraint is our goal as a Mars. And the second is we need to take into account which technologies we can certify during step-by-step activities. Therefore, if we are going to asteroid, we need to understand what is the final goal of asteroid destination. And the second one, we need to understand technologies to be used on the next steps. This is a driving for decision.
Anybody else like to add anything about destination? Are we all?
I would. So I completely agree with Dan about Mars being the ultimate objective. How could you sit through that last presentation that we just got and not, go for Mars? That was really exciting. The technologies that we need to get there are really critical to make sure we have established. And each of these two nearer term destinations, Moon helps you with the lander part of the technology, which is going to be critical for Mars, of course. And then the asteroid helps you with the long duration spaceflight habitat technologies, which is also going to be critical for these long missions. So they both have a lot to offer. But even before that, if you think about what's going to happen pretty quickly when we get to the ability to fly the Orion on the SLS, you're going to have a really exciting time where we now can put people back above, low Earth orbit again. We need to have where we're going to go next, and cislunar space seems to me to be the most logical next stepping stone for that, prior even to an asteroid or Mars, or the Moon. I mean.
So in your view, we don't go to an asteroid in 2025 if we're going to put an outpost out in cislunar space?
No, I wouldn't put a time frame on it, Brian, because I think that you can probably establish a cislunar capability pretty quickly after the capability of the SLS and the Orion coming online. So it really comes down to what would it take then to establish an asteroid mission after that. So I don't know about the time frame.
Mm-hmm. SLS on the current schedule is going to be making its first manned flight, I think, around 2021. There are a lot of folks who would argue that no matter where we intend to go beyond LEO, if we're going to go in any sort of sustained way, we definitely need a heavy lift rocket. I wanted to ask the panel, is a really big rocket like SLS truly necessary for conducting human missions beyond LEO, or could we make do with EELV, Ariane 5, Proton, Falcon 9 Heavy? And I'd like to maybe direct that question to Clay and Mark. Clay?
Thanks, Brian. Well, look, the question of how heavy is heavy or how big is big, the Apollo architecture was done because we were in a space race and the destination was close, relatively close. Could you do it with an Ariane 5 or an ELV? You could. Obviously, it's going to take a lot more flights. It's going to take in-orbit assembly. It's going to take a launch tempo that's driven by what the program is set up with. You could do it, certainly. But I think a larger rocket affords you certain things in terms of, look at the shuttle and how we were able to construct the space station. You launched elements of the space station with rockets like Proton. We've launched ATV to the space station. You certainly can do it. There's no argument there. It could be done. It's really a matter of how you set up the program, what are your goals, and how much do you need to put up there over what kind of time period. A lot of that demand is driven by both the program as well as politics, quite frankly. And what's the speed of that program? What kind of multi-year budgeting do you have to be able to accomplish something like that? So, what I would caution against is you read a lot about launch rates and economies of scale, and I know this is an international crowd, but we have this expression from Yogi Berra that it's deja vu all over again. You don't want to get into the scenario, I think, with the shuttle program where there was a big promise of a huge flight rate and lower costs that were going to drive out of a flight rate of 30 or 40, something like that, flights per year. You need to be realistic about that. Flight rates, certainly there is an economies of scale at work. There is efficiencies that come with increased flight rate. The difference between flying 1 or 2 missions a year or flying 10 missions a year is certainly relevant. The reliability tends to go up the more you fly, for sure. But when you get past, let's say, 10 flights a year, there's a big question about whether or not that price can come down and where that curve is, the elasticity and on that curve. So I'd caution against sort of reading too much into those huge flight rates.
Mark, your company has thought a lot about what's possible with existing launch vehicles. I know you're kind of focused on low Earth orbit, but could you share your thoughts about capabilities for beyond LEO?
Sure. I think one of the things that sometimes is overlooked is that these may not be mutually exclusive kind of activities. We, budget aside, which is certainly a big question. The idea of having a strong LEO capability for transportation at a lesser cost than we've seen in the past might enable the ability to do assembly, to do work in LEO that could enable the next phase of where we want to go beyond that. And I think that there's perhaps a dual path here as we're sorting out what the SLS might be. And I'm a fan of believing that we should go well beyond LEO and there should be some heavy lift capability to take us there. But perhaps that architecture in the future can be enabled also by having a strong LEO-based activity that might be something that we use to assemble in LEO, part of what that program looks like in the future. Because it's not just sending one flight somewhere, it's sending a flight and sustaining some activity in a distance. And I think as we look forward, how do we do that? Perhaps there's a way to strengthen a heavy lift rocket by bringing some of those costs down by using a different type of architecture in LEO to help enable that. And we believe that that's a process in the future that can be seen by using a lot of the existing architecture, the Arianes, the Atlas families, and the Delta families to create that ability, so that if and when we do take off beyond LEO, there is a capability that allows us to sustain that beyond just the one or two big rockets that we might be able to do a year.
Dan, would you like to add something?
If I might, Brian. I agree with Mark. There are different parts of the architecture and different functions to be executed and different ways to go about that. And so I think the spectrum can be applied to help get us beyond low Earth orbit. Ultimately, all of our analyses show that when you look at the payloads and the activities that you want to carry out, whether that be at a near-Earth asteroid, ultimately at Mars, or in cislunar space, that the 70 to 100 metric ton capability is first of all kind of a break point. There is particularly when you look at it from a volume and a packaging and a logical, how do you put the payloads together? When you go to a larger Mars mission, that's when that starts driving the need for a 130 metric ton class vehicle. So it's a matter of what function you want to execute, where in the architecture you're executing it, and then how do you go get that function completed. And you got to sort out which launch vehicle is best serves that purpose. And the reason we're working on SLS now is because all of our studies show that to get the payloads that we believe we need to put out there to go execute the missions, the mass, the volume, and the packaging constraints show us that we need to go the path that we're on.
Dan, were you involved in any of the studies or familiar with any of them where NASA looked at, they kind of assumed kind of a flat budget scenario going out to the future. And they looked at what they could do in terms of exploration if they devote the lion's share of that to SLS versus what they could do if they took an architecture that was based on smaller launch vehicles and then put more resources into either on-orbit propellant depots, more on-orbit assembly. I'm wondering if you could speak to that trade a little bit about why NASA ultimately decided to go with the heavy lift rocket as opposed to kind of spreading out its investment across a broader array of capabilities.
Be glad to, Brian. We initiated some studies, particularly back in the 2010 timeframe, and we've been through a couple cycles of what was called the Human Exploration Framework team. In those studies, those were the studies that led us to the conclusion that the 70 to 100 metric ton class is what we needed at the first break point, with the ultimate 130 when we looked at the mass and again the packaging and the volume constraints. As we went through that analysis, we looked at the options of what it would take to use the EELV and other launch vehicle options. How would on-orbit propellant depots play into that? And yes, we looked at all of those scenarios and we did that analysis against what we felt like were realistic budget environments, flatline budget type scenarios, to see how we could do this. And as we went through all of this and we tried to account for the development, the schedule, development risk, safety of the crew, as well as understanding what the infrastructure costs were that we would need to have, that we'd have to execute all this, we arrived at the conclusion that the first steps we needed to get in place were the launch vehicle and the spacecraft. And so we chose to initiate the SLS and the Orion activity. The remainder of the architecture work is still being performed, and we're still sorting through those trades, trying to understand what's the right thing to do. But it's important to remember that, particularly when you talk about on-orbit propellant delivery and containment, that there's a lot of technology work that needs to be done, along with just getting the infrastructure in place. So all of those trades, when you look at all of that, all of the elements of the cost trade have led us to where we are today, and we're continuing to sort through what are the next steps beyond SLS and Orion. And we do all of that work against what we feel like are the potential budget scenarios.
Mark, Sierra Nevada is working on a launch capability that the United States had for 30 years with the space shuttle, but now everybody seems to be working on a capsule. There's no shortage of capsule designs out there now. I'm wondering if you could tell us just a little bit about why you think a winged vehicle needs to return to the world.
Sure. I think oftentimes when we get into processes of evaluating programs, there's a pendulum that happens. So the shuttle at one point in time had a lot of challenges, and there were people who believed that perhaps that wasn't the way to go. But now we look back on the program, 135 flights, a lot of successful activities, and there was a certain set of skills and capabilities that design enabled that we would not be where we are without it. We started our program 7 years ago now to, we think, take that soul, that activity from the shuttle and move it forward to a different level. A lifting body winged vehicle has a number of attributes that we think are very valuable. The first is we built the space station not to be an observatory in our view. We built it to be a laboratory. And the idea of being able to return critical cargo as well as recumbent seating for crew to a runway within hours, 6 to 8 hours from leaving the station, we think is a very important thing. We land on a runway, we're accessible, the vehicle's accessible as soon as you land. So the idea of being able to maintain the downmass cargo capability of what we do in space is quite useful. But it goes much beyond that. The ability to do work in space, servicing missions in space, things like repairing the Hubble telescope, which was done through a combination of a terrific vehicle, a lot of guts, and some very smart people who put it all together, are things that are very necessary in space. Should we get to the point of what we just discussed about doing some type of assembly in space, the ability to be able to do that, to act as a long-duration platform for science, to act as a platform for being able to do test work. These are all things that are enabled, we think, by a lifting body. And our view is not that it's an exclusive one way or the other, that there ought to be a blend. Every other thing that we do, we have multiple types of ships, multiple types of aircraft, we have multiple types of vehicles in our military and our civilian service. So to go out and not have a capability that has certain attributes that really are quite useful, and the idea of being reusable. The shuttle had, even its complex nature, it had an average of 27 flights per vehicle. And we think that that's a pretty interesting statistic when you look at it. The Discovery, I believe, had 39 flights. So if you're looking at the long-term cost of what it would take to be in space for the next decade, as far as I know, it's almost been 55 years of capsule work going on, and not one capsule has returned to space in its current form. Pieces of it have gone up. And that's not a knock on either one. We just think that there's an ability to blend the two to make sure that NASA, as well as the space industry, has the capabilities of both at the same time.
Clay, you mentioned deja vu. 2004, 2005, the situation was the United States was talking about building a rocket, actually a family of rockets, and a deep space capsule. That's kind of where we are now. What does this leave for the rest of the world to contribute to a Beyond LEO mission, assuming we can agree on a destination? I'd like to hear from Mr. Direction on this as well, but Clay, what does this leave for Europe to build, for example?
Well, there's a lot of questions right now in Europe. Europe is tussling with a number of things leading up into the ministerial next fall over what's going to be their future for launch systems for Europe. So on that plate is an upgrade to the Ariane 5, which we're currently flying 48 successes in a row, and trying to increase the capability of that system and keep the price, let's say, relatively where it is today. Increase the capability and have a reignitable upper stage. So that's one of the options out there. Then another is a next generation launch system, which would be more akin to a modular system for single launches to GTO, but also could do, let's say, up to about 7 or a little over 7 tons of capability, maybe 14 to GTO, maybe 14, 15 to LEO. Right now we can launch over 20 metric tons to LEO with an Ariane 5. We've been doing missions to the space station. We've already done 3 cargo flights with the ATV to the space station. We also obviously are operating now the Soyuz vehicle from French Guiana, from Europe Spaceport, and the new Vega small launcher. So we have a range of capabilities. We're going to be doing the James Webb Space Telescope mission in cooperation with ESA and NASA in 2018. So we're looking forward to that. We've done a number of missions. I should say Europe has done a number of missions, Earth escape missions, missions to Lagrange points. So we have a lot of capability and a lot of familiarity with doing missions beyond low Earth orbit and even beyond GTO, which is sort of our bread and butter. Where that definition is going to come down, I think, is going to depend a lot about where the governments agree to do different types of cooperative programs. Obviously, there's a lot of room for international cooperation. I think personally that international cooperation is going to be key to getting us beyond LEO with human missions and even robotic exploration missions. The political element of that is, again, has been very tough to see the follow-through. And quite frankly, we need to have reliability. One thing that ESA affords is sort of multi-year budgeting and the ability to sort of stick with some of their programs. We need to see some more certainty on that in terms of picking the missions, the destinations, and then having the wherewithal to stick with those plans and going forward. I think there's a lot of capabilities Europe and the U.S. can cooperate with quite well over that time period if we can stick to it.
Mr. Direction, what's attractive to Energia in terms of contributing to a Beyond LEO mission?
First, probably I need to remind you, we have a lot of experience within International Space Station, and this experience to be used for exploration. We now, if we take into account first module which was launched in 1998, we now more than 10 years permanent crew capabilities on the station. And we have very huge integration experience to be used for exploration. To my understanding, space exploration program should be international under definition. The reason for this is very simple one. We have cost of 1 kilo on, as an example, on the moon orbit, about 20 or 30 times more than on the low orbit. No country can conduct this huge program by own. Therefore, it should be integrated program under definition. And we have a lot of experience for integration now. But to my knowledge, if we are going to space exploration, the integration should be more deep than now. Now we have American segment and Russian segment. And most of our hardware duplicate each other. It's very fruitful for failures, for safety, for reliability of the program. But it costs us a lot. And we probably cannot accept this budget for exploration. And instead of to use this segment approach, we probably should go to deep integration on the level of subsystem technologies. It's a challenge for us because we have not so easy experience within this integration. As an example, we spent a couple of years in discussions of the international docking system standard. We have now starting discussions about bus standard and other standards. We should have a lot of international standards and common interfaces agreed upon. It is not so easy, but it's a challenge and we should overcome this. This is first issue. And second issue, you raised the question about SLS. It's natural limitations for SLS. If we should deliver crew to the moon orbit, it should not be less than 70 as an example, better 100 tons. But to my understanding, SLS is a brilliant idea, but for the program we should have at least two SLSs, two kinds of SLSs, two kinds of heavy vehicles, because to put program on the just single launch vehicle, we can repeat our mistakes in the future. We cannot be on the position when some failure can stop huge program. This is mandatory for us, and according to this situation, we are working now on the manned crew for the crew vehicle for long destinations for exploration, and probably I hope we will go not so fast as you, but we will develop heavy launch vehicle too.
Is Russia looking to do this on its own, or is there a big carve-out for international contributions?
To my understanding, the program must be considered as an international. Therefore, it should be international contribution. But it's another glory, another challenge for everybody, because our, can I say, interdependence should be more deep than within ISS. If we are going to Mars, as an example, with crew, we cannot stop the program. We cannot accept some country decided to stop. It's another situation. It's technically impossible. Therefore, we need to create some mechanism which can be fruitful for the program and allow us to continue independently from some political decisions. This is absolutely mandatory for space exploration. We cannot stop lunar base if it's international.
I follow you. Let's talk a little bit more about ISS. And Mike, you have a similar experience. We saw where the space station today isn't exactly what we thought it was going to be at the beginning. NASA has dropped elements, Russia has dropped elements, Japan has dropped elements, but at the end of the day, it all worked out. But what Mr. Direction is proposing is that we go further than discrete elements, further than having somebody contribute a HAB module,
deeper.
Or propulsion module, yes, deeper. And by going deeper, that interdependency becomes, well, much more interdependent.
Yes.
So I'm wondering if you could speak to that. Do you think that's possible? I mean, for so long, NASA's approach, and this was in part driven by their experience during the 1990s on space station delays, was to try to keep international partners off the critical path of very big programs. We saw that to some extent with James Webb Space Telescope. ESA's contributing a launch. If they had, a launch can be switched out without as much harm to a program. So have we seen the pendulum shift on this? Do you think it's possible for us to do what Mr. Direction is proposing?
Well, yes, I do, frankly. And I think it's interesting that in maybe 10 years ago, the lesson learned from ISS might be that you want to avoid interdependence because we were thinking about delays at the time. Mm-hmm. But I think the reality is what we've really learned is that interdependence is what makes us stronger. And I would tell you that today, coming out of the ISS program, interdependence is probably a core lessons learned for something that we value. And so if you go back and look at how the program began, we in the United States started with a design. Freedom, if you remember, was the design that we had in the United States, and there was some interdependence there at the time, but not with Russia. And Russia had a different design based on the Mir, and they had a set of modules that they had designed. And what we did is we integrated those two systems together which really led to a lot of the design that we had. It was dictated by what our heritage was from each of the different partners that were coming together. And so the interdependence that we had ended up being modular in nature, just because of the nature of the design. I think what Alexander's proposing is that as we move farther away from low Earth orbit, the supply chain becomes more and more challenged. And while we had good redundancy on ISS and in low Earth orbit, and that's helped us on many occasions, it becomes increasingly difficult to afford that redundancy of systems. Having two different ways to do carbon dioxide removal, for example, may not be affordable when you're on your way to Mars. So this really leads you to thinking more about deeper interdependence and maybe looking at it at a subsystem level, like you were suggesting, Brian. And I think that this is possible to do. We do have some examples on ISS where we did do some of these things. You can think about things like the common berthing mechanism, for example. The partners all use these mechanisms. So it can be done and has been done, but I think what Alexander is proposing is to go a little deeper into that same model.
How do we manage this new type of relationship? I mean, is it time to revisit the no exchange of funds principle that guide most international programs? Is it time to start talking about creating an international space agency modeled after ESA? Do we need new structures, or do we still just try to do this within our same kind of organizational framework that we have now? Have you given any thought to that?
Actually, that's probably a better question for Dan.
For Dan?
I would say, but...
or I could put Clay on the spot for that one, too, because Clay, of course, has a lot of experience with bringing many parties together in a international context.
Look, on a typical...
I'm sorry.
Go ahead.
I'm sorry. There are two opportunities we have for this. First is to repeat something like intergovernmental cooperation. We have on ISS successful but very heavy, very difficult. And I cannot imagine we can avoid this. Hopefully, but it's impossible. Second, we have experience like sea launch. International companies in space, but commercial. Therefore, to my understanding, if we have some commercial field of activities, we can create international joint venture. If we have no commercial, because it's absolutely new technology with risk and no return, in this case, government should go. In this case, we should respect governments. Therefore, it might be ESA, but to my understanding, we should use ISS experience.
Dan, is my suggestion that we revisit no exchange of funds, is that naive given how popular it is in the United States, particularly with NASA's political stakeholders, that NASA's paying Russia for Soyuz flights currently?
Well, let me go back to your question. Let me be clear. I'm not going to establish agency policy sitting here today. I think Mr. Gretchen makes a very good point. I think we need to start with the accomplishments and the lessons learned from the space station activities over the last couple decades, and build from that. Whether we need new structures and new policies, I leave that for future debate. But I think the one thing that is clear is that space station and how we've accomplished and even had in some discussions we're having on some lower level type of partnerships, I think we can use today's structures. We do have some policy questions that we have to work around and figure out how to deal with, particularly in data sharing and how we work through things. But I think the one thing I know is that I see the buildup of the desire to go work in partnership more and more, build from the station experience, And Mr. Bolden has said it, that we are willing to go further in building those partnerships and building on and getting more interdependent in order to make those partnerships work. And I think that's something that the agency, from a NASA perspective, we're working toward, we're willing to do, and we're looking for those opportunities. Now, it's hard to get sometimes the desires and the motives all to line up in the right direction, but I think if we keep working at it, we'll continue to make progress.
I have a question from the audience, and just a reminder that there's no cards, and you can also text the number on your screen, and these questions will come up, and I'd like to leave adequate time for questions from the audience, but I'd like to work this one in now, because Dan will pull you out of the policy realm and put you safely back into the engineering realm.
Thank you.
Are Orion and SLS being planned for future international participation, such as standardized COM interfaces?
We're working right now. Our COM interfaces. We're working through our SCAN activities within the Mission Directorate.
You said SCAN?
SCAN.
What does that stand for?
Spacecraft. Oh gosh,
Well,
Baudry's
you just
going to
say
get
what it
mad
means.
at me.
What does it just mean?
It's our communication network, teachers'
Okay.
communication network.
Sure.
So we're working through all of that. We are working with ESA on a couple of things where we're in discussions about service module activities for Orion. We haven't gotten into any detailed conversations yet around SLS, but we are looking for those opportunities because we recognize that we're all living with budget constraints here in this country as well as around the world, and we have to find we all want to go do the exploration mission, and so we have to find better, more creative ways to be able to take advantage of the resources we do have. So I think we are continuing to look for those opportunities, be it government-to-government conversation or company-to-company conversation, commercial conversation. We're open to the opportunities out there, and we're looking at them from both Orion and SLS, and drawing it in through the global exploration framework activities, the global exploration roadmap. The very reason we're having this conference is to generate opportunities to continue those conversations and take them deeper.
Well, it seems like one of the things that NASA no longer has on its plate, but did under Constellation, probably still necessary, is some type of Earth departure stage. Is the SLS architecture being designed with that kind of add-on capability in mind, even if that add-on capability comes from overseas, from one of NASA's partners?
Well, I think right now in our configuration studies that we're working to with SLS, what we refer to in the SLS world as the upper stage with the J2X engine is fundamentally modeled after the Earth departure stage that we had under the Ares construct. Similar performance, the ability to restart, etc. So that is in the mix. Upper stage conversations, we are open to opportunities and discussions along those lines from international partnerships, not only at the stage level, but at the subsystem level.
So with the upper stage that NASA is planning to evolve to get to that full 130 metric ton capability, that will allow you to send Orion to beyond LEO destinations.
Well, actually, the 130 metric ton is really focused on the cargo missions. Mm-hmm. The Orion spacecraft, right now the whole system we're designing to be at this point is human rateable. We're leaning toward right now having Orion fly on one configuration and then the other configurations be cargo oriented, particularly as we get into the larger and further out missions.
So what's left for non-NASA partners to contribute to a mission beyond LEO? And that seemed to be one of the kind of criticisms of Constellation, is that there wasn't very much left for anybody else to do.
Well, I think we still have a lot of open other elements we need to go execute an exploration mission. We have deep space HABs. We have landers where appropriate. We have transfer vehicles of some form or another. And as we go through the architectural trade studies with our international partners and internally, those elements, those future elements that we need for exploration, that's where we see a lot of open trade space, particularly for international partnership.
Okay, thank you. There was another question from the audience about International Space Station, and then I have a number of questions here. And I wanted to start with directing this to Mike and to Alexander. What is government and industry doing to ensure that the lessons learned and the technologies that we developed in the construction and operation of the space station can be applied to beyond LEO destinations, whether it's like a cislunar outpost, a lengthy asteroid sortie, where we're not going to have a huge space station with solar arrays spanning the length of a football field, for example. So how do we make sure that the work we're doing here is extensible to some of these other goals?
You want to start, Alexander?
I can. Thank you. Thank you for the question. We started from the beginning to develop technologies that might be used on the low orbit and beyond low orbit. And now we have on the station a couple of technologies to be used on the, as an example, on the Lagrange point, or might be developed and used on the Lagrange point. And we have some plans. We can share our plans with community. As an example, Roscosmos made decision to develop scientific power module for Russian segment. And we consider this module as a first step to have similar module on the cislunar orbit. The model have to have some subsystem which should be used for long duration and deep space missions. This is module to be test. The technology is to be tested first on the ISS, and then within new module transferred to as an example, to Lagrange point. It's just one example. The next example, we're proposing to NASA, to community, to develop the program which allow us to certify 3 types of technologies: medicine technologies, crew training technologies, and design technologies for long duration missions beyond low orbit. And finally, we are going to test and to simulate Mars expedition on the ISS, to spend 1 year on the station, as an example, or more, then go to Earth, and then return to the station and to spend 1 year on the station one more time. This will be something like testing of Mars technology. It's just 2 examples of our approach. We have much more.
Mike, with the title of Director of ISS Utilization and Exploration, I think you've probably spent some time thinking about this as well. So how do we make sure that space station really does provide a good foundation? And beyond, what we all know about lessons learned from working together on orbit assembly, lengthy operation, do you just hand over your binders to the cislunar folks on life support systems and comm and thermal management, and they just build a smaller version, or do you need to use this time we have left on space station to actually maybe even test some technologies on the outside of the space station, on the inside of the space station?
Sure. And I think, thinking about lessons learned, I think we all know, handing a book to somebody, writing them down in a book, you can get a little bit of transfer, but it really happens through people. You have to take the people that have been involved and have that experience and get them also involved in the new experience as well. And I think we all know that. We're doing that today. We're working with all of our industry partners. We're working with our government partners to make sure that all of these people are thinking about the future as well as fully utilizing ISS today. So it starts with people, but there are a lot of things that we're learning, and I think some of these things are very important. Our ECLS systems, I'll use this as an example. ECLS, as we know, the life support systems are what will keep the crew healthy all the way to Mars and all the way home. And we are learning a great deal about ECLS today on ISS. And the studies that we've done, and involving our partners, Hamilton Sunstrand was a big player in some of these studies. And I know Ed Hodgson's out here somewhere, so if you want to corner Ed, he'd be a good person to talk to about this. What we believe is that the systems we have today on ISS are fully adequate to take care of what we need for the crew all the way to Mars and back. So we already have the capabilities in the ECLS world to be able to perform that mission as far as closing the loop on ECLS. What we need is we need the systems to be extremely reliable. So what we want to do is we want to take these systems and continue to refine them and improve their reliability so that we can count on them for these really long missions. So that's the kind of thing that we need to do. But I would also say, Brian, that there's a lot of work going on in LEO today that needs to continue for a while. We're learning new things medically that we didn't know. I'll bring up intracranial pressure as an example. We've recently rediscovered, I'll say, because I think that there was evidence of this back for decades probably, that some of our crew experience problems with intracranial pressure buildup over time for longer missions. It doesn't happen to all crew, it happens to some, and so we're trying to understand this in the medical community right now. But this is an example of the kind of thing where you think you have it all sorted out, but then you really need to make sure that you've finished the job. So I think there still is a lot more to do in LEO.
With Steve Squire's opening in the morning, I'd be remiss if I didn't ask a question that touched on at least the robotic elements of exploration. And I wanted to kind of bring up that earlier this month there was a workshop out at the Goddard Space Flight Center, and it was focused on telerobotics and the potential to extend human cognition to the moon, to Mars, near-Earth asteroids. The idea is that instead of having to painstakingly plot every move of your rover, you can have a human in real time joysticking your exploration. So the idea is that you can explore a lot faster and you can respond to changes. I'm wondering, right now we have the ISS, and later we're going to have Orion. So starting with ISS, is there any potential to use ISS to demo this type of telerobotic activity? Is there any, and even better, are there any plans to do so?
Yeah, absolutely. I think the Europeans have a plan called Meteoron. I think Meteoron will do this exactly, Brian, and this plan is already underway. So using ISS as a test bed for technologies is a really critical aspect for the program. And I think that telepresence as a technology is one way that we can potentially take our human cognition close to our destinations without having to spend all the money to actually put the crew on the surface right away. As we work towards that, we can get close to the surface by bringing people close and using telepresence to operate robots in a real-time environment. So.
Dan, can we put Orion in orbit around the moon and have the crew operate a Google Lunar X Prize winner?
We could do that, and we're looking at ways with Orion, and that's that's part of the discussion that we have in some of the cislunar space studies that we have going on. We've talked, we've also had some very early conversations about doing that kind of work around the surface of Mars. Also, get humans into orbit around Mars and be able to do that telepresence work from there also. So it's certainly in our thought bucket to go look into.
Do you think you could do it with Orion as envisioned right now? I mean, is there just enough space inside the capsule that you could add the capabilities? Could you use Orion's comm systems, or are there a lot of add-ons and you would have to wait until you had some sort of service module to go along with Orion?
Well, I think everyone, we have to remember that Orion is being designed for 21 days of crew capability. Orion in the architecture is really meant to get the crew to a hab or to a certain place, and the deep space hab, as some of us call it, is where the crew lives and works, similar to the space station model, lives and works to go execute whatever mission we're doing at that point in time. So the capability would be put more into the deep space hab, but also we would have to have some sort of integration of that, of some particular functions into Orion. But most of that work would be done in the deep space hab at the whatever destination we end up at.
Mike, just to kind of bring it back to telerobotics for a minute, then I want to get on to a different topic. Could you, on space station, would you use like TDRS to command rovers that are in the American desert or something, or up near, up in northern Canada? Could you use TDRS, or would you have to go direct S-band, and kind of what kind of limitations would you be facing with that kind of demo?
I wish I was more familiar with the meter-on experiment than I am, but I think you could use TDRS. You will get a little bit of a delay through that relay link, but it won't be too bad. So I think that you could do that. Yes, and I think that's the plan, but I'm not absolutely sure.
All right. Another question from the audience, and keep them coming. We have a few more minutes left for questions. And I'm just going to direct this to the panel and let whoever's brave enough answer it. Is there room, political will, for an international launch vehicle? Is there the political will for us to try to build an international launch vehicle? And I see a fellow who has some experience building international launch vehicles. There's a number of them here, but let's go to Clay first.
I'll get out of the way.
Why not? Why not build an international launch vehicle? We're already building international launch vehicles today. I don't want to speak for my colleagues at United Launch Alliance, but they're using various international components in the Atlas vehicle. I think Orbital Sciences as well, in Antares, is using various international components in their vehicle as well. So I don't see why that's out of any realm of possibility. In fact, if you look at commercial aircraft, there's all kinds of international cooperation in terms of engine development in commercial aircraft. If you look at the Liberty launch vehicle that we're involved in with ATK and Astrium, once we sort of decided to go down that path, it was in a matter of less than half a year that we were able to put together the proposal to bid to NASA in the CCDev competition on that vehicle. There's a lot of things that could be done. And in fact, during the course of that program, when we sat down with our engineers, and we did it all under TAAs, so if there's anybody here from the State Department or Defense Department, it was all licensed, all that cooperation and activity, and we were able to get the, ATK was able to get the licenses to have those exchanges and discussions, so it can be done. People say it can't be done, it can be done. And what we found is when the engineers got in the room together, there was a lot of commonality, a lot of common understanding that existed about taking the core stage of the Ariane 5, putting it on top of a solid booster built by ATK, and making that into a viable space transportation system. So it can be done. I think there's a political capability to do it. It's a matter of making sure that both sides of the equation are comfortable with that kind of cooperation. Once the signal is there for companies to actually go and cooperate, it can be done quite rapidly, in fact.
Is it different, though, when we're talking about a unique capability, something that doesn't exist right now, like a 130 metric ton launcher versus another satellite launcher, with each nation has its own capability?
I know. I mean, look, there's no doubt that launch in and of itself is a strategic capability of nations. People, or I should say nations, get into it for a certain set of reasons. They want that capability to be able to put satellites into orbit, or in some cases to put humans into orbit. It has a lot of international prestige. It has strategic capabilities for national defense, for civil, for weather, for all kinds of comm and other areas where it's important navigation that provides that strategic capability. But when you're talking about space exploration, human space exploration to points beyond, that's something that we all aspire to. I think we talked a lot about international cooperation, how this could be done in cooperation with Russia, with Europe, with other, and the United States and other partners. It can be done, and I don't think there's anything that should stand in its way. The ISS is a testament to that.
Mark, Dream Chaser is not envisioned is not being pursued as a entirely made in America launch vehicle. So what's been your experience with kind of opening up new venues of cooperation?
I agree with Clay in the sense that there is already examples of this happening. I think the dozen or so countries that have built the ISS at the cost of $100 billion or more, that's a pretty big example of how cooperation can happen. From our perspective, we think that as we're building our vehicle, We are inviting other countries to be part of that process because we think eventually the vehicle can be a global vehicle in its sense, no different than a Boeing or an Airbus airplane that's being used around the world for different purposes, being built in different places by many countries. And the idea of how we get it to space, we have a booster that we're working with in the Atlas V, but there's no limitation to being able to look at other boosters at some point in time if other countries are engaged with this process. So we do see it as a global exploration project, and our company's view is that while it starts off as a NASA project in terms of what we're doing at the current moment, the idea eventually is that it becomes a LEO servicing vehicle for whatever capabilities are necessary, and that is a global capability. And that may mean at some point that the people that we're working with would like to launch it on some other type of booster, and if appropriate, we'll do it that way as well.
Dan, Clay mentioned the ESA Ministerial this fall, some of the decisions on the agenda, launcher decisions, ISS continued barter agreements. What's on NASA's calendar for, let's just say, the year ahead, the rest of this year, in terms of engagement with international partners about roles folks could play in beyond LEO missions? Is there anything very specific that you guys have happening in the next several months?
We have a few things. I think, first of all, from an overall agency perspective, and I'll look at it from the overall human exploration perspective, obviously all the space station work continues, and the utilization of space station, as well as the architecture analysis work with the international partners that we've been working very closely along the way that led to part of this conference. The other activities, I mentioned the service module conversations that we have ongoing within the Orion program. We've started one conversation that's a little bit further out in terms of the SLS, in terms of fairings for a cargo variant of SLS. So we have those activities going on. We've had some initial exchanges in a bilateral form with various agencies, and we're continuing right now from an exploration perspective. What we're really working on is making sure that we have the right engagement and partnership in how we develop the architecture, bring the international partners in, not go to the mode that Professor Squires talked about of somebody sitting there saying, you do this, you do that. More of a bring everybody in, let's sort through what needs to be done, what are the options to go about it, and what can various international partnerships bring to the table, and sort through that. And those are the activities we have ongoing in the near term.
Thank you. Well, we've reached the end of our allotted time, or as the Car Talk guys would say, you wasted another perfectly good hour. But I want to thank the panelists for all the perspectives they shared.